Hello everyone, I am Urvi Mehta, Assistant Professor at B.H. Gardi College of Engineering and Technology. What we were discussing in the last video was MSI combinational logic circuits. Okay, what was the objective of this? Objective was to implement any combinational logic circuit using the two types of MSI devices, that is decoder and multiplexers. In the previous video, we learned about the functioning of decoder as well as implementing or designing any combinational circuit using a decoder. Our today's topic of discussion is multiplexers or selectors. So what do we mean by multiplexing? Multiplexing means transmitting a large number of information units over a small number of channels. Fine. So a digital multiplexer is a combinational circuit which selects binary information from many input lines and directs it to the single output line. So a multiplexer is a device which has many inputs and a single output. Now which path, or we can say which input to give a path to output, that depends on the selection criteria, that is which particular input line we are selecting to give a path to the output. Fine. So normally a multiplexer has n selection lines, 2 raised to n inputs and a single output. N selection lines, 2 raised to n inputs and a single output. Okay. So let us understand what is a 2 cross 1 multiplexer. 2 cross 1 means it has one selection line and 2 raised to n input, that is 2 raised to 2, that is 2. So we have I0 and I1, 2 inputs, one selection line S0 and one output Z. Now the functioning of multiplexer is such that whenever S0 is 0, that is it is active low, then we get output Z as I0, that is path is provided to I0 to redirect it to Z. Similarly, when S0 is 1, we get Z is equal to I1. Okay, now what we want to do is we want to see what is the block diagram of 2 cross 1 multiplexer, Carnot map and its truth table. Okay, so we are having total 3 inputs over here, I1, I0 and S0. It is a selection line but it is also input. So whenever we draw a block diagram of a multiplexer, then it is a 2 cross 1 multiplexer. So one selection, to data select, let us bifurcate it as this is a selection line, this is a data line, and all of these three combine to form the input lines. So in total there are 3 inputs and 1 output. Okay, so 3 inputs, so 2 raised to 3, that is 8 combinations, and the outputs. So whenever S0 is 0, whenever it is I1 is 0, I0 is 0, but whenever S0 is 0, what we will get at Z is I0. So whenever S0 is 0, what we will get at output is I0. Similarly, whenever S0 is 1, what we will get at output is I1. So whenever S0 is 1, Z is equal to I. So if we just fill up the K map using this truth table, then we are having 1 at 1, 2, 7 and 6. Okay, so we can make a pair, 2 pairs. In total we will get 2 pairs. One is I0 into S0 bar and one is I1 into S0. It is S0 bar into I0 and S1 into I1. Fine. Okay. Similarly, we can understand the truth table and equation of 4 cross 1 multiplexer. 4 cross 1 multiplexer, so it has two selection lines S0 and S1, and there are 4 data lines I0, I1, I2 and I3. So in total there are 6 input lines, and the output of any multiplexer is always fixed, that is 1. So whenever S1 and S0 means whenever it is 0 0, I get I0. Whenever it is whenever it is 0 1, I get I1. Whenever it is 1 0, I get I2, and whenever it is 1 1, I get I3. So Z is equal to S1 bar S0 I0 plus S1 bar S0 I1. We can derive this using the K map, and we can fill the K map using the truth table which we discussed for the 2 cross 1 mux. Similarly, for 8 cross 1 multiplexer, we are having 3 selection lines, 8 data lines, so in total 11 input lines and 1 output line. So we can similarly have the equation for it. Fine. Okay. Now, one of the important thing is we can implement a 2 raised to n cross 1 mux using 2 raised to n minus 1 cross 1 mux. That is, what is done over here is we have implemented 8 cross 1 mux using 2 4 cross 1 mux and 1 2 cross 1 mux. Fine. So, an 8 cross 1 mux, what an 8 cross 1 mux required is, it requires 3 selection lines as we saw, and 8 data lines and 1 output. So we are splitting up this mux into 2 4 cross 1 mux. I0, I1, I2, I3. These are the 4 data lines of the first mux. Similarly, I4, I5, I6 and I7. These are the data lines of the lower mux. The selection lines for this remain same, that is S0 and S1. Okay, now the output of these two mux are again multiplexed using a single 2 cross 1 mux. The selection line for it is A, and we are having 2 data for it. So finally Z is nothing but either this or this, depending on the selection line A. So whenever it is 0 0 0, I will be getting I0. Whenever it is 0 0 1, at that time I will be getting 1. Similarly, if it is 1 1 1, so 1 1 means output of this mux is I3 and output of this mux is I7, but here 1 is selected, so this particular input of this mux, that is 2 cross 1 mux, will be given a path to output. So this is one of the possibility of representing a 8 cross 1 mux using 4 cross 1 and 2 cross 1. Okay, now let us see one example of this. What is the example? We are having a 3 input function A, B and C, and its SOP form is given 0, 2, 6 and 7. So there are 3 inputs, so I need 2 raised to 3 cross 1 mux, that is 8 cross 1 mux. Okay, now at 0, 2, 6 and 7 I am having 1, so I am tying I0, I1, I6 and I7 at 1 and rest of it to 0. Now depending on the selection, that is A, B and C, I will be getting the output over here. Fine. Okay. Now one of the important thing is, that is the alternate representation which we discussed. We can implement this the same function using a 4 cross 1 mux. Let us see how. So this is the same truth table which was there in the previous slide. Now as you can see here, that if we provide this is a 4 cross 1, so there are 2 selection lines. Let these 2 selection lines be A and B, and whenever A and B both are 0, output I am getting is complement of C. Whenever it is 0 1, output I am getting again is complement of C. Whenever it is 1 0, no matter whatever is C, the output is 0. Whenever it is 1 1, no matter whatever is C, the output is 1. So instead of using a 8 cross 1 mux, I can use a 4 cross 1 mux, where the third selection is given as a data. So C bar, 0 and 1. So this is how I can get a output. Fine. So this is how we can implement any given combinational circuit using a multiplexer. Okay. Thank you.